This is the solution to the PDEs 2013 exam, question 4. So question 4a, 4a part 1, use the Taylor series expansion to derive this second order difference approximation. Okay, so as with everything involving finite differences, we start with the Taylor series. Okay, so I'm going to just write it out in terms of x plus h, y. Okay, so this should be familiar to you by now. It's quite easy to remember. And don't forget the truncation error. So highest power of h. Okay, so that's to third order. So the truncation error starts at fourth order. Okay, in order to derive this finite difference approximation, we also need ux minus h, which is the same as ux plus h, except instead of h we have minus h, which essentially means the odd powers of h are negative, the even powers are positive. Okay, so in order to, what we want is we want an expression for this second order derivative here. So I'm going to summing the two series. Okay, so this on the left we have the left terms added together, and on the right, so we've got lots of uxy. Okay, notice the odd terms cancel out. Okay, so we're left with h squared, second derivative, and plus the truncation error. So rearranging to make the second derivative the subject. Okay, so just going to rearrange this one to make this term here the subject. Okay, quite simple algebra. Okay, and don't forget the truncation error. So truncation error of the series is big O h to the 4. Well, we're divided by h squared, so including truncation error is h squared. Okay, so that shows that this is a second order difference approximation. Okay, part 2 of the question. Okay, so using what we derived in part 1, write down the equivalent approximation for uyy, and then derive a finite difference scheme for Laplace's equation. So to save, well, for interest of brevity, I'm going to use subscript notation. This essentially means instead of writing out the full sort of function, I'm going to use subscripts I and j to denote x and y. So ui j plus 1 means x, y plus h. And essentially it's the same as in the x direction. Okay, so Laplace's equation, so we sub into Laplace's equation. Okay, so Laplace's equation is a double derivative in terms of x plus a double derivative with respect to y equals 0. So if we use our finite difference approximation from before, okay, again using subscript notation just for brevity. Okay, and what we need to do is rearrange to make u, I, j the subject. Well, if we multiply both sides by h squared, obviously we just get rid of the denominator. We got minus 4 lots of uij. Okay, so if we rearrange to make uij the subject, we've got 1/4. Okay, and then the summation of all the other terms, so the one above, to the right, below, and to the left. So the one to the north, so to speak, plus the one to the east, plus the one to the south, plus the one to the west. And that's your finite difference scheme for solving Laplace's equation. Okay, right, part B of the question. Okay, here we got a square plate that satisfies Laplace's equation, or the temperature on it satisfies Laplace's equation. Okay, we're given the we're given the temperatures of the boundaries, and we're going to use a diagram with a 4x4 grid over the plate, and so label U at the grid point. Okay, so this is 4B. Okay, so what we're going to have is 4x4 array of nodes. Okay, and the top temperatures at the top 10, temperature on the left is 20, temperature on the bottom is 0, temperature on the right is 15. Okay, so there's our grid. Notice I'm bothered with the corner nodes. They're not going to be used in any calculations. Okay, and these nodes in the middle, these 4 ones here, these are going to be unknown. These are what we're solving for. Now this node down here has an I value of 0 and a j value of 0. As I move across, this is going to be I value of 1, j of 0. So if I move up, that's going to be I equals 1, j equals 1. So that's u1, 1. If I move across, I'm going to have u2, 1. If I move up from u1, 1, I'm going to have u1, 2. And across, I'm going to have u2, 2. So that's my, well, simplified domain, or simplified discretization. Why is a small grid useful? Small grids are useful because we can, essentially, because we can perform a pen and paper calculation. And that's to verify that if we were to write a program for this to perform the calculations, but it's correct. So for verification purposes. Okay, so that's that was 4B part 1. Part 2, implement Jacobi iterations for the finite difference scheme. Now, the key thing about Jacobi iterations is they always use old values. Okay, so the k plus 1 estimate, so this is our improved estimate, is equal to 1/4 times the values to the north, west, sorry, north, east, south, and west from the previous, well, current estimate k. So these always use old values. That should be plus. Doesn't actually matter what order these go in, but I tend to go north, east, south, west. Okay, so if I was to perform this calculation, u11, okay, and in doing so, I tend to always assume that the initial values of these are 0. Doesn't matter what initial values you start with for an elliptical PDE. Okay, so u11 is going to be 0 plus 0 plus 0 plus 20, all divided by 4. So that's of course 5. u21, go back to the grid, I'm going to have 0 plus 15 plus 0 plus 0. 0 plus 15 plus 0 plus 0. So that's a quarter of 15, which is 3.75. Okay, do the same for U12. We get 10 plus 0 plus 0 plus 20. So that's a quarter of 30, which is 7.5. And finally for U22, it's a quarter of 10 plus 15 plus 0 plus 0, which is a quarter of 25, which is 6.25. Okay, so that's one application of the Jacobi method. Of course, in practice, we do the same thing again and repeat calculations until these converge. Okay, and part 3 of the question, repeat the calculations using Gauss-Seidel. Now, Gauss-Seidel method uses values when they've been calculated. So what we're going to assume here is I'm assuming a row by column order. What that means is the nodes to the bottom and the left have already been calculated for the current iteration. So, i.e., nodes to the south and west are known for the current iteration. That's what I'm assuming. I'm also assuming same 0 starting values. So if I write out the Gauss-Seidel method, so again we've got 1/4, it's a node to the north from the previous iteration, or current value I should say, the node to the east, oh, that's a J, the current value, plus the node to the south. This time we know what the value is in the current iteration, in the k plus 1 value, so I'm going to use that, and the node to the west. So slightly different from the Jacobi method. Okay, so if I perform these calculations, now the first one I do is going to be exactly the same as the first one for the Jacobi, because I don't know any of the values yet. Right, okay, now the second one, okay, if I go to the north plus the node to the east plus the node to the south, now the node to the west is this one here, which I've just calculated, so I can use that. Okay, so that's also 5. Okay, and U12 is 1/4. Okay, the node to the north plus the node to the east plus the node to the south, which is this value here, plus the node to the west. So what's that? That's a quarter of 35, which is 8.75. And finally the U22. Okay, so node to the north plus the node to the east plus the node to the south, which is this one here, which is 5, plus the node to the west, which is this one here, which is 8.75, which equates to 9.6875. And that's a single application of the Jacobi method.